projects going on with, let's say, Tata's, a lot of PSUs, banks, L&T, Boeing, Google, Microsoft, Siemens, Murata, Volkswagen, etc., etc., etc. Many. And then now we got Center of Excellences. Center of Excellence. So we had the right. So if I come to different, just to give a glimpse of the activities, we have got nano electronics, network and research and applications. We got advanced mechanical testing facilities. We got National Center for Photovoltaic Research and Education at IIT Bombay. We got a Center for Propulsion Technology. Apart from different departments I'm talking about, that there are several centers. The National Center for Excellence in Technology for Internal Security. This is related to defense, internal security, terrorism, etc., etc. Then we got a new Center of Machine Intelligence and Data Analysis for C-Mind. We got Electrochemical Energy Laboratory, where the battery research has been started now, because you know now electric vehicle becomes the norm for the future possibly. Then we got a research for fuel cell activity. Then we got a center where for entrepreneurship, where we believe that IIT Bombay believes that yes, entrepreneurship is a very important. Many of you will be interested in time to come. Then we got a Center for Learning and Teaching, how to teach, how to learn, also is an exercise. Then we got Center for Teaching Empowerment through workshop, seminar, training, and we got a big project that we did for 1 million solar study lamps. In addition to all this, we got various activities for students. We got IIT Bombay racing team. We got driverless car project going on, which is from Mahindra. We got a underwater robots, which is Matsya project. Then we got a Shunya project to create net zero solar power houses. We got a Pratham satellite, as you know, which was launched by IIT Bombay, and it was actually launched on board the PSLV C-35. So all these activities have been happening. And if I talked about futuristic scenario, if I talk about technology transfer, we got a technology transfer done in various ways. For example, we got indigenous telecom routers in last 3-4 years, wastewater heat exchangers, for example. Lot of technology generated in the labs ultimately have been licensed to industry so that they reach out to the common man. During COVID time, we have come up with a lot of technologies and they have been transferred to industries. And ultimately, we all believe that, yes, this technology should be going out to the public at large. So whatever research you do, ultimate aim is to actually reach out to the public, and ultimately IIT Bombay runs on the taxpayers' money. So we all believe that this money should go back to people, develop depending on the technologies that we have been developing here at IIT Bombay. We are called Institute of Eminence. IIT Bombay has been called as Institute of Eminence because of which we get additional funding from Government of India, and under which we have got some focus area, which is nanofabrication. All the chips that we make should be done with nanofabrication technique, materials and advanced manufacturing, health science and engineering, data and information science, and sustainable chemical agencies sciences is our focus for under the Institute of Eminence norms. I know it is a lot of knowledge thrust upon you, but very important that you are joining the bandwagon, you are joining our research process. And during the coming 5 years, 4 years that you are here, you should see that you work on different projects. Please approach various professors, try to understand what excites you. And this can go across departments. Even if you are from metallurgy department, you can work in chemical department, computer science department, mechanical department. You can form a team of students. Do a project. Don't waste your time here. These are the 4 very important years of your life. Find a small project, work with a professor, go to the lab. If you go and ask a professor that I would like to work on some project, nobody will say no here basically, because everybody wants student to work on this problem. But it all depends on your enthusiasm. So make best use of these 4 years. Go to the professors, and when you come with BTech final year project or MTech final year project, you should actually know what kind of project you want to work, what kind of area that you want to, whether you want to work on solar energy, for example, or fuel cell, or batteries, or new heat exchanger, or new fabrication technique, new manufacturing technique, or want to, for example, or develop algorithm, that kind of thing, or new material, for example. So please take care that you time when you are physically here, actually try to contact. So meanwhile, when you are away from this place, please try to go to the website, try to see which professors work in what area of your department or other department also. Then you can actually think that what excites you. So this event today is basically to enthuse in you, to understand what kind of projects delight you, what kind of things you get attracted towards, or what is that you basically feel excited about. No doubt when you start learning in a class, the professors will actually try to excite you. But I'm sure with the 12th class learning that you have and the JEA that you have cracked, I'm sure you know that some courses do excite you. For example, physics, applied physics, engineering physics. There is nothing called all physics, chemistry, mathematics in an applied form that we have here. All right, and biology, of course. So all these are very important topics, and I think today's session actually will let you know what kind of work is happening at IIT Bombay and how public at large, society at large, is getting benefited from IIT Bombay. So I'll stop here. I don't want to take much of your time, and I again wish you all the very best, and again congratulate you that you are making it to IIT Bombay. Thank you very much. Muskan, please take it from me.
Thank you, sir. Guys, just a couple of instructions. You're requested not to spam the chat box. Just put in whatever questions or comments you feel are relevant to the talk. And the attendees are not allowed to unmute themselves. Also, they cannot see the other attendees, so don't worry about that. And so put your questions in everyone's chat. Don't send your questions personally to the speaker or to the panelist. Carrying further, for the first research talk, I'm glad to welcome Professor Anindya Dutta from the Department of Chemistry. His research interests include photophysics of fluorescent molecules, excited state dynamics, ultra-fast processes and silicon nanoparticles, etc. Handing over to Professor Dutta.
Thank you, Muskan. Good evening, everybody. It's a pleasure, as always, to be here today. It is just that it would have been better if we were all together in Hostel 15 mess, and if you could do it in the way that we always do. Okay, let me just share my slides. Where is the share option? The share option is disabled. Muskan?
Sir, just a second. We'll make you the presenter.
Okay.
Sir, you have been given the sharing rights. Could you, are you able to share now?
Yeah, give me a sec. Um,
Uh, yes, sir. Like I have made you the presenter.
yeah, wait. I think I've come out of the window. I don't see the thing anymore.
Sir, are you able to share it now? Have you
No,
made
not yet.
presenter?
Muskan, why don't you start with Varun and maybe I can go second. I'll go out and come back. Is that okay?
Okay, sir, no problem. So for this talk, I would like to welcome Professor Varun Bhalerao from the Department of Physics. Professor Bhalerao is an alumni of IIT Bombay with a BTech in Electrical Engineering. His research interests lie in astrophysics, X-ray and optical studies of transient sources, neutron star binaries, etc. So handing over to Professor Bhalerao.
Okay, let's see if this is working fine. Hello, everyone. So I am Varun Bhalerao. Let's see. Can you see my screen with this great video of IIT Bombay playing in the background?
Yes, sir. We can see your screen.
Okay, great. So, whoa, this is quite interesting. Every time someone sends me a message, I actually get a ping in the background. Wow. So everyone who is typing yes for whatever, if you could please stop, that would be very nice. Thank you, everyone. Okay, so we actually would all like to do this differently, right? Usually when we do this event, it's you are all here on campus, on this nice, beautiful campus where you are seeing a bunch of clips about it right now, and we would all actually be sitting together in one of the hostel messes, as Professor Dutta pointed out. And this would have been a very informal face-to-face conversation. But you know what? That's not the situation. So we could actually spend a lot of time sitting here and whining about how being in a lockdown sucks, or we can actually go forward and have this discussion anyway, right? So I choose the latter path. So I'm Varun Bhalerao. As you were told, I am actually from here. I did my BTech in electrical engineering. I graduated in 2006, and then I decided to switch to astrophysics. So I went and did my PhD in astrophysics, and now I'm back here doing astrophysics at IIT Bombay, and that's what I'm going to talk to you about for the next 10 minutes or so. I'm sure a bunch of you are wondering what exactly is the purpose of all of this. Will we be doing projects in first year, and what is exactly going on here, right? We are not even going to be meeting these faculty members for at least another semester. So the point here is that we are welcoming you to the family, and we want you to know what exactly your family is like. This is your new family. This is going to be your home for the next 4 years, and we want you to know all aspects of it. There are various student bodies that will be talking to you about what they do, and then it's only appropriate that we also tell you about what we do. I'm sure there are many of you who are just very surprised to see that there exists astrophysics at IIT Bombay to begin with. So I'll tell you what kind of stuff we do, right? IIT mein kya chalta hai? Well, here is a nice example just to get you started. What you are seeing is a beautiful time lapse taken by Dr. Shubham Srivastava, who was a postdoc at IIT Bombay. You see the Milky Way rising over a telescope dome here, and this is the Growth India telescope that is located in Ladakh on Mount Saraswati. Growth India, this is a 0.7 meter telescope, and it's the country's first and so far only fully robotic telescope. And the entire automation work of this telescope was done by undergraduate students just like yourself. Okay, so I hope those of you who were chatting away and having fun will now have some idea about this, that we are talking about serious stuff. We are talking about undergraduate students getting involved in world-class research, and this is one of the smallest research telescopes in the country, but it is also the second most productive telescope in the country. And IIT Bombay is responsible. IIT Bombay and Indian Institute of Astrophysics Bangalore together set up this telescope, and we are responsible for a lot of the operations and a lot of the research that goes on from it. I am getting a few messages about my voice being unclear. I can't help it, unfortunately. We have several hundred students connected, and some of you will experience flaky connections. This is also being recorded, and you will be given links to the recording later. Okay, so chill out, बैठो आराम करो, हो गया जी, टेंशन छोड़ो थोड़ा, IIT में आए हो अभी, sit back, relax, hear whatever you can. There is always time to catch up with the rest later. Okay, so Growth India Telescope is just one of the many projects that we work on. Growth is a partnership between 15 institutes spread all over the world, many in the US, Israel, UK, Taiwan, Japan, Australia. We collaborate with a lot of universities around the world. And if 15 universities is not enough for you, then we can actually step up the game. And IIT Bombay is a part of this little experiment, which some of you may have heard of. It's called LIGO, Laser Interferometric Gravitational Wave Observatory. Of course, I'm sure all of you have heard of it. It's been responsible for Nobel Prizes and whatnot. This is a flypast of the LIGO detector at Hanford, and there is going to be a LIGO India that's going to be set up. IIT Bombay is a part of this massive international collaboration. We have people who work on many different aspects of gravitational wave detection over here. In addition to that, what my own specialization is actually, so here is animation of two neutron stars that are spiraling around each other, and as they spiral in, they emit gravitational waves, but when they finally collide, there's a massive explosion, and in that explosion you end up releasing a lot of X-rays, gamma rays, radio waves, you name it, all kinds of electromagnetic radiation. And it is this that we actually study with Growth India and other telescopes. Now, one of the telescopes we've been using uh, quite strongly for all of this is a satellite called AstroSat, which just finished 5 years since launch. So AstroSat is India's first space observatory. I was part of the team that built AstroSat. In particular, AstroSat actually has 5 different telescopes which cover the sky from optical, then ultraviolet, soft X-rays, hard X-rays, low energy gamma rays, everything. Okay, and this particular instrument called CZTI, which you see over here, we actually are a very active part of one thing which you should realize very important is that at IIT Bombay, there is always room to dream larger. Okay, so if you are talking about using a satellite, why limit yourself at that? As Professor Atreya said, there are many student teams, and there's actually a student satellite project. IIT Bombay students built a satellite called Pratham, and it was launched several years ago, and they are now working on its successor called Advitiya. And then if students are doing this, of course, faculty are not going to be left behind. So we have this extremely ambitious proposal called Daksha. So this is going to be a set of 2 satellites. What I have in my hand here is a small 3D printed scale model of the satellite. And we will make 2 of these. They will, of course, actually be about a meter across, about 2 meters tall. And these satellites are going to be about 10 times more sensitive than the current world's best satellites. So we are talking about a mission like SWIFT, which was built by NASA. There's a mission called Fermi, which was built by NASA and ESA. And we want to take completely in India, build two satellites, which will be a factor of 10 better than this, right? You don't want to go 10%, 20% better. We want to do factor of 10 better than this. And this is a very ambitious project led by IIT Bombay. There are people from 4 different departments working on this, people from physics, electrical engineering, aerospace engineering, and mechanical engineering. One of them, Professor Siddharth Tallur, will be talking to you shortly. And then we also have collaborations from several institutes around the country, including TIFR, PRL, RRI, IUCA, and of course ISRO. So this is the kind of stuff we do. And then comes the important question about how we do it. So this at the top here is a picture of the astronomy, cosmology, and gravity group at IIT Bombay. This is a dated picture. We haven't taken a group photo for a while, but there are 5 faculty members involved, 1, 2, 3, 4, and 5. You can find out more on the physics website. Here's an international conference we hosted about 2 years ago. We had people coming in from all continents representing here in this conference. But it is not just about those. Here is what we have been doing in the lockdown, for example. So here is my group. Say hi, everyone. And all of these people have actually been working on various projects. 3 of these people are postdoctoral fellows. There are 3 PhD students, and everyone else is a master's or a bachelor's student right here. And in the last 6 to 8 months during the lockdown, in addition to their academics, they've been nicely working on research. And some of them have actually just submitted. So when you do research, you publish your results as a refereed publication, or what is commonly just called a paper. So let me point out which of these people have actually submitted papers recently. So this one, 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 this one. And yes, of course, I have also submitted one. And that makes you wonder, well, what are the rest of them doing? Several of them are actually in the final stages of completing their research papers. So let me mark out those as well. This one, this one, this one, this one, this one, and yeah, that completes it, right? So we are talking about very serious stuff here. We are talking about you as undergrads getting involved in world's most leading projects in any aspect that you want, and you actually have the potential to make a big impact, to make a big difference. And that's what all of this is about. So I will end with that. Okay, I'll give you one quick example. Some of you may have seen this news clip. This is 2 students who discovered the closest asteroid that flew past Earth without actually hitting it. And this, I've put this example in here specifically to point out that these 2 students, I'm a physics faculty working in astrophysics, and the students are from departments of mechanical engineering and metallurgy. Okay, so your background, as long as you're willing to work hard, doesn't matter. Here's a movie made with the Growth India telescope of another asteroid. You can see it's speeding past several stars. And that's about it. So I'll leave you again with this nice time lapse. Here are a few websites that might be of interest to you. And again, welcome to IIT Bombay.
Thank you, sir. So now I can take up some questions from the chat.
Okay,
There's a question by
yeah,
yeah.
please read it out. That's what I was going to suggest, because I can't see the chat box since I'm in full screen.
Yeah, okay. So there's a question by Shreya. Are there any foreign universities or organizations with which IITB is coordinating in terms of research in astrophysics and cosmology?
Okay, so the short answer is yes. So we are, as I said, Growth Collaboration has 15 universities. LIGO has few hundred probably. We are also in other areas of physics. We are part of CERN and so on. In addition to that, let me answer that question a bit differently. There are foreign universities who are collaborating with IIT Bombay for research. Okay, mark the difference. Daksha, the satellite which I talked about, is going to be so sensitive and so ambitious that we have people from Caltech, we have people from NASA, we have people from Amsterdam, from Tohoku, and a bunch of places around the world who actually approached us and are collaborating with us leading that research. Next question.
Okay, so there's a question related to the same. Are we also working on research with organizations like ISRO or DRDO?
You can go back and watch the recording, right? I just talked about how we are doing major projects with ISRO. There's also a lot happening with DRDO. And in addition to astrophysics with ISRO, we actually have an ISRO cell on campus. We have a lot of different ISRO activities that are taken up on campus. And you can look for the space technology cell of ISRO at Iit Bombay, and you'll find more details on the website.
Thank you, sir. So now we can move on.
Thank you.
Thank you, sir. I just wanted to check once with Professor Anindya. Is he available now? Professor Anindya Dutta?
Yes, and now the share button works. Thank you.
Okay, sir. Thank you.
So while my slides load, let me start talking. That's okay. Welcome to Iit Bombay, and your very first interaction with us is something that obviously many of you are wondering what's going on here. Why are we even talking about this? We are talking about this because Iit Bombay is not just a college where you get your undergraduate degree. It's a prominent research institute of the country and the world. So, is my slide visible?
Yes, sir, it is.
Yes.
Only problem is that it's not moving. But anyway, the first slide itself, even if I cannot show any other slide, perhaps the first slide is enough. So here, the purpose of the exercise here today is to let you know what kind of research is done, and perhaps to tell you what research is all about. Because, I mean, right out of school, we don't really expect you to know what research is and why people should get into research and all. Professor Atreya has told you about one aspect of research. What I'd like to tell you is that one should not get into research unless one is terribly interested. And let me try to explain why I am sort of speaking against party line in this. So this cover that you see here, I hope many of you would have read this book. The name of the book is Jonathan Livingston Seagull by Richard Bach. Small novella. Those of you who have not read it, I strongly recommend that you do. So this is about a seagull, and the name obviously is Jonathan Livingston. Now, as we know, all seagulls fly, and they fly because that is how they get their food. Seagulls fly to catch food. Jonathan Livingston was a seagull who flew for the sake of flying, because Jonathan wanted to learn the art of flying and wanted to excel in it. And the other, not very sure if it's completely appropriate example that I have in my mind is that for those of you who have watched Breaking Bad, in the last episode, Walter White finally confesses why he had done what he had done. Well, what he had done is not good. But finally he says that he did it because he was good at it and he liked it. So to cut a long story short, that is why we do research. Because research is all about asking a question nobody else has ever asked and trying to find out whether it is possible to answer them or not. Right. Obviously, my slides are not moving, so I'll just do it without that.
Professor Anindya, sorry to interrupt.
Yeah.
I have your slides. I can present on your behalf.
That'll be great. Please do it.
Muskan, you can give me presentation, right?
Yes, ma'am, we'll do that.
Ma'am, I've given you the presentation, right?
Is that visible?
I think it's coming up. Yes. Can you please present? Yeah. So the only thing is that this first slide does not have Jonathan Livingston Seagull, but that's fine. I've already spoke about it. Can we go to the next slide? So as you see, we are in the opposite extreme compared to Varun. They try to explore things that are ultra big. In our group, we try to follow processes that are ultra fast and that are ultra small. When I say ultra fast, I mean things like times like femtoseconds and picosecond, 10 to the power minus 15 second, 10 to the power minus 12 second. And the question that naturally comes is that what is the need to measure such short times? We need to measure such short times because chemistry actually takes place in those time scales. The time required for a bond to break is something like 270 femtoseconds. So the very fundamental processes of chemistry do take place in that time regime. And to measure such a small time regime is not very easy. As you'll understand, if you want to measure something that is happening very fast, we need a stopwatch that will go down to that time regime. And to generate a stopwatch that can go down to picoseconds and femtoseconds, it has taken humanity a long time. What you see here is the famous arrow of time taken from the Nobel lecture of Professor Anand Rao, who got his Nobel Prize for working in ultrafast chemistry, what he called femtochemistry, in 1999. And here you can see that from 1980 onwards, we have the capability of measuring femtoseconds. And Pratibha, next slide, please. And using these femtosecond lasers, what Zewell's group had done was something beautiful. They took what they called photographs of a bond breaking. Without going into the detail of the instrumentation, what this curve here shows is how the population of sodium iodide decays. And the reaction that's happening is that you start with sodium iodide and then it breaks up to give you free sodium and free iodine. So the population of free sodium increases with time, population of sodium iodide decreases with time. And if you look at the x-axis, full scale here is 8 picoseconds, which means within 8 picoseconds, it is all done. Not only that, you see that it is not a smooth decay. It is not a smooth rise. Rather, what you see is some oscillation. What that tells us is that sodium iodide doesn't just break like this. So tries to break, and then the atoms come back, tries to break again, comes back again, and slowly this, with every iteration, the separation increases until the atoms are set free. This was the classical experiment, one of the classical experiments done by Professor Ahmed Sewell. And whoever is interested to learn more, you can read an easy version, something that we all can understand, even in Atkins' physical chemistry book, the book that we are going to refer to extensively while teaching CH107 physical chemistry to your first year class. Next slide, please. Now, I told you that we need very good stopwatches in order to go down to such small time scales. And what you see now on the screen are the stopwatches that we use in our lab and in our institute. If you want to measure times in nanosecond, 10 to the power minus nanosecond, then we use this technique called time correlated single photon counting. The instrument that you see on the left top So this has been our workhorse for a long time. What you see is a new one, which has been installed only last year. If you want to measure smaller times, then we use one of the two instruments called femtosecond optical gating and femtosecond transient absorption. Of course, these are very, very expensive stopwatches, and they have been set up with generous funding from the government as well as the institute. Next slide, please. And using these, what we try to do is we try to understand what happens in small times. Not only that, we are interested in finding out what happens in very small volumes. What is the chemistry that takes place inside a living cell, for example? For that, last year, we set up this facility of what is called fluorescence lifetime imaging and microscopy that allows us to measure ultra-short processes inside ultra-small volumes, like cells or aggregates of polymers and molecules and stuff like that. What you see here is the picture of pollen grains. Of course, pollen grains don't look like this. So all the color that you see here is pseudo color. This is added by taking into account something called fluorescence lifetime. But let that be the story for another day. Let's go to the next slide. Let me tell you what we have done using these instruments on two kinds of systems. In our group, we have mostly studied molecules, organic compounds, but over the last 6-7 years, we have also started looking into what are called nanoparticles. Nanoparticles are particles of small little particles of nanometer size. So that's what the name means essentially. And they are very useful in many applications. Different nanoparticles are used for different things. You could put nanoparticles on your shirt and make it super hydrophobic so that you go out in the monsoon of Bombay, your shirt doesn't get wet or your umbrella doesn't get wet. You could use nanoparticles to make self-cleaning surfaces. But our interest is really in working with semiconductor nanoparticles. So far, we have studied two, cadmium selenide nanoparticles and cadmium sulfide nanoparticles. These have immense use in two different fields. One is to make solar cells, and the other is to work as markers for biological events. So what we have done so far is we have worked with this very nice looking nanoparticles. This is of course a cartoon, but these are called nanotetrapods. Those of you, well, of course, everybody has studied some chemistry in 11 and 12. You know that in organic chemistry especially, we love this shape of tetrahedron. Methane is a tetrahedron. So here, these are larger tetrahedrons compared to the atoms, to the molecules. These are tetrahedrons of nanometer size. And this particular shape gives it a lot of advantage. What we have tried to see is that how you can play around with the properties, how you can play around with the preparation of these nanoparticles so that you get the optimum amount of light coming out of it when you shine it with light. So that is what makes it useful for applications in solar cells. The other application that we're trying to see is, can it work for drug delivery? Because what these nanoparticles also do is that if you can somehow introduce them in biological systems, things like carrier proteins, this is human serum albumin, come and sit on them. And human serum albumin is a carrier protein, as I said. So it contains things like drugs. You can set the drug free using these nanoparticles. The other thing that we're trying to understand is with cadmium sulfide nanoparticles, we are trying to see whether we can make it a useful marker. To understand it, we have unraveled the processes that take place in femtoseconds and picoseconds in this nanoparticle so that we can make it fluoresce or make it photoluminescent to a much greater extent than what it normally is. Next slide, please. That is one part of the work. The other thing that we are very highly interested in is organic molecules that give out light in solid state. And the application is something that I don't have to explain to this generation. As you know, organic electronics is here. Things like OLEDs have become part of our daily life now. And for all these applications, what you really want is you want organic molecules that emit, give out light in solid phase. And that is easier said than done. Next slide, please. We have a lot of conventional fluorophores, molecules that give out light when in solution. The problem is when these molecules come together, then a lot of interaction happens between the molecules so that they don't give out light anymore. So it is like you sit in a class, if you talk to each other, or if you're busy populating the chat room, then you don't really follow the lecture, right? Same thing happens with organic molecules. If they're close together, they interact with each other, and whatever excess energy they might have taken up by photoexcitation or by excitation by electricity, that energy doesn't come out as light anymore. That is dissipated in the surroundings. So this has been circumvented over the last 10-15 years, next slide please, by using what are called fluorogenic molecules. Molecules that do not emit light just like that, but you can, under certain conditions, bring them together, and when they are together, then only they fluoresce. These molecules are ideal for applications in organic electronics. Next slide. So what we have learned in this field so far is that we have worked with a particular class of molecules. Let's go to the next slide, please. Thank you. And what we have seen is that all these molecules are very often flat. And when they're flat, you bring them close together, they can sit on each other. This is called pi-pi stacking. And when that happens, the fluorescence is destroyed. So using one class of molecules, we have established that you have to prevent the molecules from coming close together. How? By doing small little chemical modifications so that the molecules no longer remain planar. If you can make them puckered like this, then that works. If you bring in some metal ions, that works many different ways. The other kind of molecules that we're working with, this has a very big name. Let's just call it DBMPT. And here you see these are photographs. This left one is DBMPT in acetone. That's a nice solution. The molecule exists in monomeric form. Here, what we have done is that we have added water. So now water is a bad solvent for this molecule. So now it starts aggregating. And then when it starts aggregating, you can see this bright orange fluorescence. And we found using electron microscopy that it forms actually small little nanorods which are photoluminescent. Next slide, please. And then one thing you want to do in organic electronics is that you want things that give out light, white light. So we could combine it with another molecule, and you see this looks like a light bulb, doesn't it? You see very nice white light coming out of it when it is irradiated by ultraviolet light. Next slide. Then all that was done using something called surfactant. Surfactant is just soap. Problem with working with soap is that it is a little flaky. It's not very stable. So we thought that we'll replace soap with what are called triblock copolymers. This is the structure of triblock copolymers. In a nutshell, these are polymers in which you have hydrophobic part flanked by hydrophilic part. So we use two kinds of triblock copolymer, one in which your hydrophilic part is short, one in which hydrophilic part is long. So we see that for the shorter one, we get what are called microspheres, spherical aggregates of micrometer dimensions. And with the longer one, we get nanorods. Your diameter is in nanometer, but length is in micron. And they are strongly fluorescent. So you can use them perhaps for biological imaging. And this difference in shape has immense implication in their cellular uptake, because eventually you want to put these in cells. Next slide, please. I'm not showing you the data, rather I'll show you a cartoon where we see that with this P123, the first polymer, we generate these spheres, as I told you. No, please go back. So these spheres fail to enter the cell. It cannot cross the cell membrane. However, no, go one slide forward. Sorry, that's too. Sorry about this. But these nanorods are sort of like needles. They can actually penetrate the cell membrane and enter the cell. Not only that, they light up what are called these lipid droplets that are there. So morphology of these aggregates impact very seriously whether they can at all act as markers for intracellular events or not. Now let's go to the next slide. Let me thank all the students and postdocs, funding agencies, our department and institute, thanks to whom we have been able to do all this. Now, with that being said, what we try to show is that, see, whatever we do is sort of different from the chemistry that you've studied so far, right? Here we are, chemists, working with very sophisticated instruments, analyzing data, using computer software, worrying about applications in material science and biology. So research today is very, very interdisciplinary in nature. Here in this institute, we have a civil engineer who works on biomolecules. We have a chemist who explores the use of artificial intelligence in telling how reactive something would be. We have electrical engineers who actually do synthesis. And we have physicists who work in biological sciences. And they don't do this because they're frustrated with their field and they don't like to do what they're trained for. No. They use what they have learned all their lives to solve problems that span across boundaries of subjects. Some of you have been asking, can we do it? Are we equipped to do it? Let me tell you this. You may not know the subject. Of course, you do not know the subject after high school. But one thing that you have definitely is intelligence and the ability to learn. With that, if you're willing to learn, you can make a difference. Lots of undergraduates from our departments and from other departments have made very significant contribution in the research of our group. When can you do it? I would not suggest that you start doing it right away the moment you join the institute, but the summer between first year and second year is a good starting point. So by that time, you'll get to know a little more about what kind of research goes on and where. I think that is when you could seriously participate in research activities by yourself. Right. Can nanoparticles alter their physical properties? Well, yes, they can. Well, the nanoparticles that we have shown you, these nanoparticles are of two types. One is something that is hard, those nanotetrapods, for example. But we can vary their shapes and sizes by varying reaction time. And the second one that we showed you, this DBMPT and triblock copolymer and all that, they are self-assembled nanoparticles. By changing the condition, one can change their properties as well. Can we currently take part in any online workshop? Okay, I think these are more general questions. I'm done. This is what I wanted to talk about. Thank you very much. And sorry that the presentation did not work from my computer. So that's it. So back to you, Muskan.
Thank you, sir. It was a wonderful talk. So coming up next is Professor Siddharth Tallur from the Department of Electrical Engineering. Professor Tallur completed his BTech in Electrical Engineering from IIT Bombay itself. His research interests include digital systems, signal processing, photonics, microsystems, etc. So handing over to Professor Tallur.
Yeah, thanks, Muskan. I am also not able to see the share option. Just give me one moment. Otherwise, I'll have to request Professor Pratibha to share on my behalf.
So you've been made the presenter, so now you might be able to see the share option.
No, I do see that I am the presenter, but there is some other issue. I don't know why I'm unable to share my screen. Professor Pratibha has my slides. If you don't mind, could you please share your screen and I can give commentary?
Yeah, just a minute, Professor Siddharth.
Yeah. So until my slides are up on the screen, maybe I can sort of start talking. I have 10 minutes here. I'm very happy to get to interact with all of you sort of in whatever limited fashion we are able to do it this semester. I hope very soon all of you will be back here and then we'll have more sort of deeper interactions, right, face to face. But until then, like Varun was saying, we'll make the best of whatever we can.
So in these 10 minutes, I do not think I can give you an overview of all the different things that we work on in my research group. I'll try to give you a flavor of maybe two themes. And now I need my slides. Shall I try leaving the meeting and joining again? Maybe that will help.
You will have to make me presenter, Muskan.
Okay.
Now I've made you the presenter.
Okay. Is that visible now?
It is, but it is rotated by 90 degrees.
Oh.
Yeah.
Uh,
We need not do it in full screen mode if that helps.
yeah, I have not made it full screen as well.
I see. Let me do this. Let me leave the meeting and join again. And maybe Muskan, then you can make me presenter. I see a pop-up that says I have to restart WebEx. So hopefully that will help. Yeah, give me 5 seconds.
Until then, guys, for questions like what exactly are the research opportunities available in the institute? We have a small presentation at the end of the session for that. So kindly hold on for that question for a while.
So, if I may use this moment, I would suggest to all students that one very nice way for you to get engaged at this point is that there are many active clubs and groups on campus. So join those, okay, and that is where you will find a very, very important asset, which is like-minded peers, and they'll help you don't get answered today.
Thanks. Is my screen visible now? Wonderful. Yeah, so sorry about that delay.
Yes, it is.
Like I said, in 10 minutes, I do not even want to attempt telling you about all the different things that I do. So I'll just talk to you about a few of the things and maybe tell you why I decided to talk about these. Okay, so here's a very brief introduction about myself. I think Muskan already mentioned that I am also an alumnus of this institute and very happy to see all of you here now. After my graduation, I spent 1 year in management consulting. I got bored of that within 1 year. And then I felt that what I want to do sort of is more creative technical stuff, right? So that's why I went and got a PhD, worked in industry for a few years, and now I'm back here. We'll see where life takes me next. But my research philosophy, so Muskan mentioned all of the different areas that I work in. The common thread that ties all of them together is this sentence here, which says making sense of the world through precision measurement. So all the kind of work that we do in my group is focused on making very precise measurements, but then also application oriented, right? So our focus is trying to make these precision measurements in very low cost kind of systems. And I will show you a few examples of those in a little bit. And this graphic here sort of captures the different aspects of what we try and do. So most of our work in my group is experimental. So in any project that we do, the experiments form a large part of the effort. But at the same time, we also do a little bit of computational and theory. Not as much as the kind of effort that we put in on the experimental side. But the goal behind any of the efforts that we do is all towards quantifying uncertainty. So whenever you do any measurements, typically we hear or we are trained to sort of say that either something is working or not working. When we say it isn't working, we do not quantify sort of how much it is not working, right, or how much it is working. So with any measurement, there is uncertainty, and how do you quantify that? And sort of how do you then comment on the accuracy of the measurements, right? So that's where all of this is geared. More on that, maybe I think some other day. Why do research? So Professor Datta also mentioned a little bit about this. Here is my take. The cartoon on the left sort of illustrates why I think we should do research, right? There are solutions in today's world. All of you are lucky to be born at a time where technology shapes so much of what we do. We are able to interact remotely now, even in the middle of a pandemic, right? That would have been considered magic maybe 100 years ago. So there are solutions. It's not like we have problems and there are no solutions. There are solutions, but they may not be the most effective solutions. There is always something that we can do better. And if we are too busy perfecting the solutions of today, right, we have problems today, we have solutions that we use to manage those problems today. If we just stay happy doing that, we will never be able to progress, right, or do something better. So if we have to do that, we have to make time for research. We cannot say we are very busy doing whatever we are doing. Uh, Everyone has 24 hours in a day, but how you manage those 24 hours is up to you. I agree with Professor Datta. Do not start thinking about research right from today. First settle into the system. Maybe next year would be a good time to sort of start thinking more actively. But do make an effort while you are here. And the other graphic on the right, this one sort of tells you how research is very different from the kind of training that you have gone through so far and the kind of training that you are going to go through now in this next 4 or 5 or 6 or 7 years, right? Um, our education system, for very good reasons, teaches us to diversify in the kind of skills that we learn. So you will be taught many things. You will be taught to diversify. You will learn a lot. You will not specialize in any one topic during undergraduate. Maybe later in life you might. But research gives you the opportunity to go deeper into areas that you are interested in. All right, and you have a lot of facilities that will be accessible to you because you are part of IIT Bombay. So please make good use of those. Okay, so let me then just show you a glimpse of some of the research activities that we do. I am in the electrical engineering department, but if you just imagined what electrical engineers do, I'm sure you would not have imagined something close to what we do in my group. So this is the first project that I wanted to talk about to you. These are corrosion measurement systems. This here is a very shabbily connected corrosion measurement system. Uh, this is a coil. There is a schematic shown here. How this thing works is not very important to be discussed today. what I would like you to notice is if you keep that coil even 5 centimeters away from a steel bar, you can make out the difference between a rusted steel bar and something that is not rusted. So these kind of systems, of course, here it's not packaged very nicely, but these kind of systems we want to make handheld scanners that you can just scan on the walls of your home or the ceiling and just detect whether the rebar inside that wall is rusted or not. Or it is a very low power system. Looking at the photograph, that may not be very evident. That is okay. One thing I want to point out is all of this work, this project we started doing in March of this year. All right. And these results, these images were taken last week. And the student that is working on this project thankfully stays in Bombay. So he has been doing most of the work at his home. And now he comes to campus every now and then to do these measurements. Doing hardware projects in a lockdown, being stuck at home is possible. One just needs to have the imagination to figure out how to do that. And when the time comes, I'm sure you will also explore opportunities and you will find that people here are very happy to reciprocate and engage you in projects. All right. So this is one example. There is another example here. This is in collaboration with Professor Banerjee in civil engineering. There's a different kind of application. These are aerospace structures. What you see here is a panel that is used for making aircraft bodies. And if there are defects in these panels, you can measure them by passing acoustic waves through this panel. So again, how that is done and how the damage detection is done is maybe a story for another day. The point is, in this figure here, which is taken from Professor Banerjee's lab, this is done using a very expensive setup. So this box that you see here is a computer that's very expensive, about 20 lakhs or something like that. This again is something that we managed to get together over the lockdown. It's a very cheap board. It's a breadboarded version which still works very well, right, and costs less than 5,000 rupees and can do whatever the 20 lakh box can do. There's a lot of signal processing that goes behind the scenes in sort of ascertaining the damage. A lot of machine learning algorithms also that I do not want to talk about today, but I'm sure you will get exposed to all these things and then you can also look out for opportunities like this. The other research theme that I want to talk to you about is something completely different. This is related to biosensors. This here shows a bunch of photographs. How this sensor works, I cannot possibly explain to you in few minutes. Work that took more than 1 year to do. So let me not even attempt that. This is just an optical system. It detects the concentration of one of these proteins that is present in our bloodstream, and the concentration of that protein is indicative of some diseases, right? Mostly associated with cardiac diseases. And we made again a very cheap biosensor. What I would like you to notice is the units here. These are micrograms per milliliter of sample, and the sensor is able to resolve very nicely these very small concentrations also. We also do some bit of chemistry. So these are nanoparticles, gold nanoparticles that were synthesized for detecting the presence of arsenic in water samples. And again, this is done using an optical system. How this thing works, you just shine light through it, and when the nanoparticles aggregate, you measure the reflection at a particular color, right? So the optical properties of that sample change, which is what you can see here. So when the nanoparticles are aggregated, the color of the sample changes, and that is what we detect. All right. So these are examples of optical systems. The last slide I want to show you is again work which we started during the lockdown. This is a project which we started in April. This is in collaboration with a group in biosciences. This is a potentiostat, and this we started primarily because of this pandemic. Before April, I did not know anything about DNA sensing, and now we have done some work in DNA sensing. So all you need to get into an area or make a contribution is the willingness to learn and stick to it no matter what, right? So the pandemic threw many problems our way, but my team was very persistent and we persisted
converter. A power electronic converter is nothing but a circuit, an electrical circuit with some switches, inductors and capacitors. That is what is shown here. So, and these switches are semiconductor switches. Okay, so they can block thousands and hundreds of volts when they are off, and they can conduct a few hundreds and thousands of amperes when they are on, and they can be turned on and off or off very fast, as in like within few hundreds of nanoseconds or microseconds. So these switches are like that. They're semiconductor based switches. Some examples are MOSFETs, IGBTs, and so on. So we have a power electronic converter plus a generator which goes into this box. Okay, and there could be a transformer in some of the turbines, and that gets connected to the utility, which we also call as grid. So this is what goes inside the box behind this turbine, and we primarily work on the generator part of it. So that is what I tried to show here in the green colored ellipse. So we design and control wind turbine generators. Right now, there are two kinds of generators which are very popular in the market. One is a doubly fed induction generator based on something called induction machine. And then there is another kind of generator which is a permanent magnet synchronous generator. So these two are dominating the market. So each one has some pros and cons. So we try to explore different kind of generator configurations, new kind of generator configurations, and we are working on demonstrating the advantage of those configurations through analysis, simulation, and experimental investigations. So we design these generators and then we get them fabricated, and we also develop certain control methods to extract power efficiently from the wind turbine. That is called maximum power point tracking. And then whatever design and control methods we follow, we verify them through numerical simulations. They're typically done using computers. And we also carry out experimental investigations on laboratory scale prototypes. So one may get a question like, okay, how do you have a laboratory scale wind turbine? So we use certain emulations. So for example, we make a motor behave like a wind turbine. So for example, this right side is a generator. The left side is the pink color circle or ellipse is a motor which is controlled using a power electron converter in such a way that it behaves as a turbine, wind turbine. So that is possible. So we have this turbine that is being emulated, that's called emulation. And then we have our generator configuration that can be tested. So this is one activity, one research activity that happens in the laboratory. And then we also have a teaching experiment. I wanted to demonstrate this because this has been designed to give all the students of our department who will do this energy systems laboratory course, and this experiment they do as a part of the teaching laboratory. Okay, so we have an artificial wind generation unit, basically a blower, and then we have a small scale wind turbine which is coupled to a generator, and the power level is about 300 watts. And then we have the associated circuitry to extract power and to carry out the measurements and so on. So this will give students good insight into the complete wind energy conversion system. And then coming back to the research activity in our lab, we also work on electric vehicles, some aspects of two-wheelers, four-wheelers, and also as well as electric traction or trains. So we work on the design and control of motors, especially without permanent magnets for two-wheelers, electric two-wheelers. typically the motor goes into the hub of the wheel of the electric two-wheeler in most of the two-wheelers, but of course some have chassis mounted motors as well. And then we also work on battery management systems, like how efficiently we monitor the health of the battery, and we also control charge and discharge. Of course, we cannot control the discharge because that depends on the power demanded while the electric vehicle is running. But we can definitely control the way batteries are charged and make them more efficient or increase their life. We also work on certain aspects of high-speed electric trains and how do they affect the utility when they start drawing, because these trains draw currents of higher magnitude and there are some unwanted components of currents that are drawn. Okay. So we try to see the effects of these high-speed trains on utility. That is another activity that goes on. And another interesting work that we do is on magnetic gears. These are basically contactless gears. So you have one shaft which is coupled to the inner rotor, okay, that is the ring. So I'm just showing the cross section. And then you have the outer rotor which is connected to the other shaft. So as you see, conventional gears are contact, they will definitely have contact, but these are based on magnets. So, and the gear is designed in such a way that the movements are smooth and there are no pulsations or variations, significant variations in torque on both the shafts. So, and it's naturally overload protected because it just slips off when it is overloaded. And it has all sorts of applications ranging from space, automobile, and wind energy. So we carry out the design and we also evaluate the performance of this gear analytically from fundamentals. And then we validate the design and analytically evaluate performance through numerical simulations and experimental investigations on prototypes. Yes, somebody has typed in the chat window that Hallback arrays. Yes, Hallback arrays are improvised versions of the magnetic arrangement so that you get the magnetic field effectively on one side. Because the magnetic field that is actually going inside, the field lines that go inside, they don't really contribute to any work being done. So the field lines, if you want the magnetic field lines to be only on the outer side, you need to go to arrangement of Hallback array. It's a good thing that a student mentioned. Then we also work on certain issues of power electronic converters and AC motor drives. So we look at the improvement of the life of electrolytic capacitors, because electrolytic capacitors are one of the indispensable elements in these converters. And then we also work on some control methods to improve the performance. That is all I can say at this moment. And there are certain new switches, semiconductor switches. So traditionally, silicon has been the material for power electronic switches. But recently, there are some new materials that are being used and some commercially available products have come. They are based on silicon carbide and gallium nitride, things like that. So we try to develop power electronic converters using these a new kind of wide bandgap semiconductor switches. Yeah, so that is all I had to say about the work that we do. Thank you, and I'll be happy to answer questions.
Thank you, sir. It was a really nice talk. So there's a general question in the chat. How the research in energy science different from that done in electrical, mechanical, and chemical departments, as generally energy is considered as a mixture of all these departments?
Okay, yeah. So different aspects of, so you, let us say for example you consider you consider electric vehicle as an example. So if you want to, and the electric vehicle has different components. It has battery, which is the energy storage element. So if you want the battery to carry more energy per unit volume in the given volume, because you have a restriction on volume and weight, right, in an electric vehicle. So if you want your battery to have more energy that is stored, you need a person, an expert who can design such a battery and also evaluate its performance. That means you need a person with electrochemistry background, right? And the moment you have a battery which is efficient, and then you have then you need to make sure that it is charged properly. It is charged properly, and also the discharge, as far as while the battery is being discharged, you also want to maintain as much as possible that its life is also maximized. So that is where power electronics people come in, or the people with electrical engineering background will come in. So, so in energy department we have people from different backgrounds. For example, we have people from storage background, and that means where they can work on batteries, they can make batteries from scratch. And we have people from electrical background. And now coming back to this wind energy, or even let us continue with the electric vehicle itself. Let's say you have many electric vehicles and they are just being charged. For example, you consider city. In city, many people have started using electric vehicles, and you have many charging stations. So when such a scenario occurs, what will be the effect on the main utility grid? Or can these electric vehicles support the the utility to solve some problems? Like for example, there is a voltage dip, there is some flicker or some due to something. So in such case, can these vehicles support, because they are anyway part not being used? So we need people to also look at such scenarios in large systems. So in our department, we have people who can look at these large systems and also evaluate the effect on such systems. So that is one example that I can say. That is how an interdisciplinary department, or the people with different backgrounds can come together to solve real world problems. Hope that answers your question.
Thank you, sir. Coming up next is Professor Asim Tewari from the Department of Mechanical Engineering. Talking about his research interests, it includes Internet of Things, additive manufacturing, deep learning for image segmentations, etc. So handing over to Professor Tewari. Sir, you're not audible.
Yeah, Asim, you are still not audible.
Audible now?
Yes, sir, it's audible.
All right, so that's the problem when you have multiple speakers, multiple cameras, multiple speakers, and each web conferencing system has its own nice way of making sure that you're not audible. All right. So, well, congratulations to all of you for coming to IIT Bombay. Welcome to IIT Bombay. I know physically you're not here yet, but digitally you are all connected. So being late in the night, I don't really want to get and involved in boring you with lots of complex things. But essentially, I want to give you a glimpse of the activities which I do, research activities which I'm involved in, and also at the same time give you a sense of what to expect and what are the possible avenues for you to look at when you want to be in the area of research. Now, and hopefully my screen is visible. Yeah.
Yes, sir, it's visible.
All right. So I will be talking about artificial intelligence in smart manufacturing. So I work in the Department of Mechanical Engineering. I am primarily involved with manufacturing research, advanced manufacturing research, smart manufacturing research, also nowadays known as Industry 4.0. And essentially what this is all about is artificial intelligence in smart manufacturing and manufacturing. So maybe I'll just quickly walk you through some of the manufacturing research which I'm involved in. So one of the major activities which we are, for instance, involved in is in machining, metal cutting. And this is an activity which is phenomenally time consuming for aerospace applications, especially. The parts which you fly on, the aeroplane parts, are so made that 90% of the metal is machined out. You are left with only 10% of the part which you are actually using. So machining is a very time consuming and expensive activity. It thus has to be improved and has to be made more efficient for it to be cost effective. So this is one area which we are involved in a very big manner. We have some very advanced machining equipment. We have a 5-axis, high torque, high RPM machine, one of the best in the world in its class. And we also do instrumentation to that. So essentially, we are able to measure torques, forces, vibrations, acoustic emissions, thermal imaging. So what you see, for instance, is a thermal image of a part which is being machined. At the same time, we can do high-speed imaging of it. So what you see on the left is a high-speed image of a milling process. And thus we can get all the signatures of a machining process when it is being machined. Now, apart from machining and getting the signatures in situ, we can also do ex situ analysis, where we can start looking at how the chip formations would occur. How would the shear band formation occur in this material? How would the subsurface damages be there? Now, it may not be really appreciated, but machining is an extremely high strain rate deformation process. The rate at which the material deforms in machining is of the order of 10 raised to power 6 per second. This is almost like explosion. So imagine if something explodes and deforms, this is how you're actually deforming the material. But on top of it, you're also deforming it in a very large strain. Now, I know you guys must not have done a lot of stress strain, but I think stress and strain is something which you're aware of. So in machining, the strains can be as high as 180, 800 to 900%. So you could have 8 to 9 times the deformation of the size of a material. So it can go to 800% strain. So essentially, you have a very high strain rate process, which is also going through a very large energy production. So it is a very hot process because you may be producing a lot of heat because of the deformation. And at the same time, you may be having coolants which are being sprayed on it so as to cool the material. So you are having a very high transient heat transfer problem, high deformation and solid mechanics problem. At the same time, you are having a chatter and a dynamics problem because your tool, the machine tool, the cutting tool, and the workpiece is all vibrating. And all of this is playing role to give you the final machine surface. So this is extremely challenging, at the same time very interesting part of the manufacturing process. Machining is not done just for metals. However, of course, we also do composite machining. And composites is a field by itself. So this is one area which my group is involved in. A lot of fundamental understanding, just to give you some colored images, what they're about. So for instance, the colored image which you see at the bottom is the electron backscatter diffraction micrograph. So this is an electron backscatter diffraction micrograph of the subsurface microstructure. When you machine a surface, the structure below it goes through very large, severe deformation. And that deformation is what we are able to see in this machining affected zone. You can also look at the shear band, which is on the right-hand side, bottom right. And that shear band could be looked at in transmission electron microscope, where you can start looking at dislocations and atomic structures. So you essentially can look at how the dislocation substructures and atoms are playing a role in the machining process, which finally results in a macro component of yours. So this is truly a very, very complex process. Many things are still unknown. The physics is unknown. Forget about the application and multi-scale linking. The multi-physics itself is unknown. So this is one activity which we are involved in. And of course, I'm not the only one. There are several colleagues of mine working in this area. Another activity which is in the composites area. Now, composites is a very big area. We are only involved in fiber composites in polymer matrix. So these are the stuff which we work on. And again, composites are used in aerospace. As you may know, the Dreamliner, Boeing Dreamliner has majority of its made up of composites, carbon fiber composites. And the carbon fiber composites have the special, I would say, weight to strain, weight to strength and weight to stiffness advantage. So they weigh very less and they are extremely stiff and they're extremely strong. And that makes it possible for you to have very light structures which will be able to withstand a lot of stresses without deforming. And that's why aerospace is going to embrace composites moving forward in a much, much, much bigger manner. This also is a huge challenge because once you are having composites made up of polymers and fibers, there's a huge difference in their stiffness, strength, and other things. And thus you have a material which is varying in stiffness, especially very drastically. When you go through the curing process of a composite, the curing results in shrinkage of the resin, and that distorts the material. As a matter of fact, the first Dreamliner, when they were trying to fit the fuselage along with the front part of the plane, they realized that the two were made at two separate places, and these were huge, of course, cylinders. They were trying to fit it together, and they realized because of distortion, there was almost 2 inches gap, and thus they could not fit. And that was a huge challenge, and that delayed the Dreamliner process for a while. Of course, they were able to get over it, and they were able to create composites which were matching up till millimeters, and so that they could be put together. So we are involved in composite process modeling. So what you see at the top are the process modeling slides: resin transfer molding, distortion-based, curing-based distortions, and spring-in. Then we produce those composites. So we are not just doing modeling, we are actually physically making composites through vacuum-assisted resin transfer molding. This is our lab, our VRTM lab, as well as we have an autoclave in the aerospace department. And then we have a 3D printing of composites. You can actually print 3D composites. This is a big thing now, especially in the area of drones, because you may be at a at a site and you recognize that you need a drone of a specific size. So you don't want to be carrying a drone which is of that specific size, because you may have a payload which is very dynamic, and thus you can actually print a drone right over there of composites, and you can fly. Then we also do characterization of composites. So we have one of the most advanced 3D tomographic facility in India. We can look at about 700 nanometer resolution in 3D, and we can create this 3D image and do a lot of different kinds of analysis, including deformation, compression, tension, and heating and cooling of it. And this facility is very unique. This is especially useful when you are looking at composites which could have defects in terms of porosities and voids in it. So this is just to show you a 3D image of the composite with those white dots as the voids. They have been circled with a red circle. Of course, you can look at the fibers at a much larger magnification, and this is showing you the fibers which are about 7 microns in diameter. And these are carbon fibers embedded in a specific resin. And they are the aerospace carbon fibers. Then you can also perform post-processing, which essentially means machining, drilling, and other things of the composites. And that is another activity. And that goes back to the previous slide where we were talking about the composite, the machining of metals. And then, of course, we also do design of components and fatigue analysis. So in a nutshell, the composite work which our group is doing starts and encompasses almost every aspect of composite: the process modeling, the actual processing, the defect analysis, the post-processing, the designing of components, and doing fatigue analysis of components. Probably very rare to find all of these activities happening in one lab. The next activity, which is again a big activity, more synonymous to smart manufacturing, is additive manufacturing. And additive manufacturing is where you really build something from scratch rather than subtractive manufacturing, where you machine things out. So you have a substrate and you start depositing your material and you build a part from it. Now, additive manufacturing has lots of advantages, but there are few things which only additive manufacturing can do, which is not possible through your conventional manufacturing. And one of them is, for instance, very complex internal structures. If you want to create internal structures, there is no way that you make a solid block and then create those internal structures. So that is something which is not possible by any other thing but additive manufacturing. The other thing which is possible through additive manufacturing, which is not possible through conventional manufacturing, is that you can create a set of alloy systems which are non-equilibrium. Now, you will be studying equilibrium phase diagrams. You may have done some parts of Raoult's law, Henry's law, and there are lots of very complex multi-phase systems which you can have in alloys. But almost all those alloy systems are essentially either equilibrium or meta-stable equilibrium phases. Whereas in additive manufacturing, you can suddenly create materials which are not really in equilibrium phases. This is a potential which has not really been exploited yet. So the future would see materials which the past has never seen. We will have material systems. Imagine suddenly you are trying to create a painting and you have just 12 colors. Until now, for centuries, we have been doing paintings with 12 colors. But suddenly I give you 500 different shades which you had never seen before. Your paintings will be far more vivid and far more, lively. And that is what additive manufacturing has done. All the traditional alloy systems are equilibrium alloy systems or metastable equilibrium. But now suddenly we can go to non-equilibrium alloy systems. And that opens 1,000 times more alloy systems than what we have so far been exposed to. We haven't been able to really explore all of them. And we are just scratching the surface. So this is one very big advantage of additive manufacturing, which just is not possible through conventional manufacturing. The other big advantage of additive manufacturing is that you could have a customized part. So every single part can be customized. Imagine you go and you buy a cell phone. There are millions such cell phones which are being produced. You buy an automobile, you buy a motorcycle, you buy a car. There are like millions of such similar exact models happening. But just imagine that the future would have where every individual will have their own customized vehicle, their own customized cell phone, their own customized watch. Everything will be customized. It would be different from anyone else's watch or anyone else's automobile. And that is possible through additive manufacturing. This would be a luxury, of course, but there are things where this is not really a luxury, but is a necessity. And one of those sectors is medical sector. When you're looking at medical implants, you want a medical implant which is exactly made for you. You don't want a medical implant which is like, okay, you buy a shoe size, either 8 fits, 9 fits, or 10 fits, and you have to be in between. If you're in between, hard luck for you. But that you don't want in medical implants. So the medical implant industry will see additive manufacturing as the game changer. So additive manufacturing has phenomenal advantages over the regular manufacturing. However, it also has lots of disadvantages. And the biggest disadvantage is that the properties of additive manufacturing and the surface finish is not as great as the conventional manufacturing. And that is where we are looking now at additive subtractive manufacturing, ASM. This is where we put the best of both the worlds, and we are able to produce things which are very, very, having the best of additive as well as subtractive manufacturing. We are also big time into cyber physical systems and artificial intelligence. We create cyber twins of our machines, which are giving live data to the cyber existence, the cyber clones of these, and you can observe the various parameters, vibrations, current, acoustic emissions from the machine. This is just to show you that as a machining process is occurring, this is the real data which is coming out. And in the center, I'm giving you the data in a compressed form, and I'm just expanding that on the left side. Similarly, the acoustic data is given on the bottom left. And this is the FFT, the real-time FFT, which we are doing of that data. And you can start seeing the physical aspects of the internal dynamics of your machine. So every machine in our institute, we would like to have a cyber twin of. In our lab, we are already building that. And thus, every machine which you have, there is a cyber twin of that available, which is copying and is giving you a live data. Sometimes the rates of our data acquisitions could be on tens and hundreds of kilohertz, because the data is really very fast and we may want to have a lot of data coming out of it. We, of course, use this for a smart factory, where we are able to monitor various activities of a factory, do operation monitoring, predicting quality, equipment condition monitoring, health monitoring, adaptive controls, and other things like that. This is a part of what we call as Industry 4.0. So we design our own IoT devices, we design our own devices which wirelessly send data. So this is our device which we have designed. We have various different kinds of such devices. And this is the data which they send wirelessly to our servers. We, of course, have an entire system where we have the hardware, the firmware, the communication protocols, the artificial intelligence-based algorithms running on the cloud, as well as the web servers which give back the data. So this is just the screenshot of our application, how it looks. These are the IoT devices installed in machines, and this is where the cloud interacts. This can be extended to many other cases. We are also looking at power management systems, so we can look at power efficiencies. What you would be surprised is that our medium and small scale industries are actually very poor in terms of their power efficiencies. We are charged not based on the actual power used, but on the apparent power used. And the apparent power used is a very strong function of the power factor which you are having. And some of these factories have very poor power factor, and they don't even know about that actually. So these are some of the things. We again have IoT devices which can optimize that. We have used this in many other areas. So the artificial intelligence which we essentially apply in manufacturing can go to many other areas as well. So one of the key things which we are working on is natural language processing for legal processes. So we are having legal chatbots and other aspects of electronic discovery happening in legal system. We are also using artificial intelligence and machine learning for new alloy discoveries. So we are trying to invent new alloy systems, especially high entropy alloys, and that is another very big activity. We are also seeing that you can replace the conventional aspects of engineering by artificial intelligence. So for instance, this is a beam vibrating. It's a tapered beam which is vibrating, and we are looking at the natural frequencies and other aspects of vibrations and trying to predict that through deep learning. This is taken further to video analytics, where we can look at postures, identify motions. This can be used for video surveillance. You can do face recognition, unique person recognition, security and surveillance. You can also do this for shop floor analysis. For instance, if the workers are working, is it leading to some hazardous situation? Are workers not efficiently working? What are the best practices? All of this can be done through video analytics without any human involvement through deep learning. Of course, this can be used in biological science, and biology is the one which is the biggest, I would say, gainer from all of this. Currently, the image classification algorithms for detecting carcinomas in histopathology are far more advanced than an average histopathological doctor. So the doctors are still required, but these deep learning algorithms are able to perform far better histopathology on carcinomas and other things. This has also been applied. So my research expands a very vast area, as you would see. It's going from all the way from machining, composites, additive manufacturing, Industry 4.0 to artificial intelligence and business enterprise analysis. So we worked with one company in trying to look at their entire process. So this is a retail chain across India. And we were looking at point of sale inventory stock, predictive analytics based on seasons, and giving them a real-time feedback on the customers who walk in using artificial intelligence. But that is not all. My students have used artificial intelligence for a very large set of varied activities, including, for instance, credit risk analysis, web analytics, looking at sports analytics, predicting who will be winning IPL, looking at aspects of stock markets. So with that, I will stop essentially. So I just wanted to give you a quick glimpse of the activities which my group is involved in, and they span aspects associated with machine learning, artificial intelligence, primarily starting from the requirement of manufacturing, but they have essentially, we have diversified to many other areas, including pure artificial intelligence and machine learning for aspects associated with various other activities. So with that, I'll stop. I'll be happy to answer any questions if there are any.
Thank you, sir. It was a really informative session. So guys, we are open to questions if you have any.
I'm trying to read the questions. I don't see any specific questions. It's just a regular chit chat going on in the chat. So maybe before closing, I want to just tell you all folks one thing. You all are very young, adults now almost, and well, you are adults now, and you need to be really open to all thoughts. There are two things which you need to be aware of. One is that future is going to be far more different from what the past was, and the only way you can be prepared for the future is to learn. And the second thing which I want to tell you is hard work. There is no substitute for hard work. Be smart, but imagine if you are doing smart work and hard work. If you put the two together, there's just no end to it. So work hard, work smart, and be ready to learn. Don't shy away from learning. Don't work for grades, but work for learning. With that, I'll stop now.
Sir, there's a question in the chat. Can artificial intelligence and deep learning be also used for psychological problems like depression?
Oh, of course, it is already being used. So actually, this is a very ethically touchy issue. So there are several websites, there are several companies which are out there right now, which are doing different kinds of aspects of therapy. We ourselves, my colleague in mechanical, has come up with ways in which he's trying to understand how to analyze and diagnose people who are having depression based on deep learning. Also come up with some kind of prognostics and some kind of prescriptions. So there are websites out there. I have an entire set of slides on how deep learning is changing aspects of depression. There is one website I want to talk about, and this is really something, I'm glad that you brought this up. There's a website which is looking at aspects of creating a chatbot which will talk to you to kind of remove your depression. And this chatbot is essentially almost like a human, and it gets to know you, and it talks to you as if you have a friend who's trying to counsel you and help you and talk to you. And there are, of course, lots of ethical issues about this chatbot, because there are things which may not be very good about it, in the sense that you don't want to be talking to a computer. But yes, AI is being used, and future is going to be very, very different. You would not know what is real, what is not, because AI would be almost everywhere around. Currently, you are pretty much sure that what you are seeing is me, but 20 years from now, it could be a artificial intelligence realization which may be talking to you and maybe counseling you and talking to you. Yes, yeah, there is no field, there is not a single field where AI is not being used. As a matter of fact, the coronavirus vaccines have AI has been used to come up with, narrow down the possible candidates. At the same time, people think that the coronavirus itself has aspects of AI which have been used to create this, if it at all is being created in lab. So So AI is something which is to be, you need to watch out for AI in future, essentially. That's the one single advice I can give.
Thank you, sir. So for the next talk, I would like to welcome Professor Sanjeeva Srivastava from the Department of Bioscience and Bioengineering. He is the group head of Proteomics Laboratory. His research interests includes proteomics, protein-protein interactions, drug target discovery, etc. So handing over to Professor Srivastava.
All right. Thank you, Muskan. I hope I am audible and my slide is visible.
Yes, sir, you're audible and it's visible.
Great. So let's welcome all the students, incoming students who are going to join very soon the campus. I'm Sanjeeva Srivastava from Department of Biosciences and Bioengineering. I'm sure you must have wondered that, what biology is doing here in this engineering campus. But given that, Professor Atreya in the beginning, the Dean R&D, has mentioned to you that this campus provides a lot of opportunities, open opportunities to really get exposure of various fields. And that is not limited to even biology or humanities. And as this Professor Asim mentioned to you, that you have to be very open to learn new things, because the way future is changing, you have to really adapt the new things very smartly. And there is no substitute than to really think about how biology is going to change the world, right? So I work in the interdisciplinary area of protein research, especially proteomics field, which is aiming towards studying the large number of protein molecules of any system, any life system. And we want to apply that on different clinical problems, especially cancer and other type of infectious diseases. For doing that, I'll just take you briefly for this field of genomics, and which at least some of you might be aware of, that how the understanding the blueprint of life, the genes, have really given a lot of boost for understanding different type of complex problems, right? Earlier, we had no idea that even what constitutes us, what makes it so different individuals from other type of organism. But now, by looking at these molecules of life, especially starting from DNA, you know that what is the genetic code of a given individual. If there is something going abnormal in the life system, is there some sort of mutation is happening? How to identify those kind of unique changes? And that's where, when you think about studying one molecule, it's probably easier. But when you want to look at thousands scale, the problem becomes much more complex. And that's what we are trying to use with the latest technologies, like the field of proteomics and proteogenomics, how to try to understand these complex systems by looking at these beautiful molecules of life, the DNA, RNA, and the proteins. And again, if you're looking at the cell and you want to screen through these molecules, if you can really understand them well, then probably you can provide very unique information for a given individual. Professor Asim just gave a very nice lecture, and also given you a couple of interesting points, that the same shoe size of 8, 9, 10 may not be flexible for each one of you. You need a very specific size which you'd like to use, right? And it's much more important in the field of the clinical field, especially for the therapeutic aspect. The same drug may not work on every individual, given that we are also different, we are also unique. And that's where the field of precision medicine comes into the play. We are looking into many of these aspects of research, which is quite interdisciplinary in nature, also quite applied in nature. We work a lot of clinicians from around the world, especially a lot of Mumbai-based doctors and hospitals, where aim is to really dissect out these complex diseases and really look at them at the molecular level. And all that can be understand in this growing field of proteomics or proteogenomics. Again, if you are just looking at some common symptom and the blood test, you cannot identify the complete picture. But if you can start looking at the exact molecule which is making the change, exact mutation, exact modifications, then probably you can give much more precise information for that given individual. Also, most of the drugs which are currently given in the clinics made by all the pharma sectors, they're all proteins. The question comes that whether the precision medicine which I'm talking is a reality. So for the time being, let me take you to the future of this field, which is not very long. You have to just wait for a couple of years' time to see how the field of medicine is going to change. So meet this future Adam, and who's going to get some treatment for he's diagnosed with cancer, and he's going to look for his treatment. So in this particular clinic, he's going to not only get his blood test done and the physical parameters being measured, but also he's going to be looked for all the changes which is happening at the molecular level, which are all genes are getting altered in this individual, which are all proteins are getting modified in this individual. So now every cell by cell is going to get a scan, and that information is what is going to be really crucial if now you want to really understand this individual at a very, very personalized level. All this process, which is very fundamental in biology, but requires a lot of engineering devices, lot of engineering based solutions, different type of big data analytical tools, and without that, it is not possible for us to really look at these complex, any biological system. So in this case, now if this particular individual who has now been diagnosed with cancer, you want to give them a drug, only one specific drug is going to work for that individual. And you want to apply a generic drug, it may not work out for every individual. And that's where you have to understand that what is really unique, which is changing in this particular individual, and is this particular drug, the receptor is going to bind with that particular drug molecule or not. And if you already have this particular type of knowledge, knowing, with the experiments, with the actual data, then what you are doing is, with the very targeted way of therapy. Otherwise, what is happening is very blinded therapy that, you're giving any kind of chemotherapy and any kind of drug treatments to any individual, right? So this is where I hope you are understanding that why we are trying to bring these concepts of interdisciplinary nature of research, where the fundamental concepts of biology, the clinical problems, as well as different type of devices, different type of big data solutions, all of that together can transform the field of future precision medicine. This is one of the very relevant cartoons, which is giving you the idea, but it's already happening in the world, and it really got big boost in Barack Obama's time when in the US, and I'm sure with the Joe Biden becoming president, it's going to much more flourish in US and other parts of world, where the field of cancer moonshot and cancer proteogenome research is really going to make huge difference. So this is not going to be any more just the cartoon, but the realistic picture. Brief glimpses of the kind of work which we do in IIT Bombay. We have set up very advanced proteomics laboratory at IIT Bombay, which is equipped with variety of instrumentation and technologies, especially different type of mass spectrometers, microarrays, next generation sequencer, heavily funded by the government and other type of industrial partners. We work actively on different clinical problems with Tata Memorial Hospital as the collaborating hospital, and we try to look into various type of complex brain tumors. As you can understand that the brain tumors are very deadly tumor. So understanding them, that what makes them so different. Also, what is the molecular feature which is really important to target. That's a machine learning type of tools are very handy for us to identify from the thousands of protein which of the proteins can be a major node for this targeting this. And then we take those targets forward for the testing them on the patient-derived cell lines or the cell culture models or the animal model to test out these, how effective these therapies could be. There's some example of another brain tumor, which is the glioblastoma multiforme. And likewise, I think we have expanded this particular field of research and partnered with other countries as well, which is now forming a consortium known as ICPC, or International Cancer Proteogenome Consortium, which is having 31 institutions, and India joined as the 12th country, which we are leading from IIT Bombay along with Tata Memorial Hospital in Mumbai. Idea is that can we take most prevalent cancer of India, especially the cervical cancer, breast cancer, and oral cancer, and try to dissect out at every individual level what are the gene mutation happening, what are the post-transition modification happening at the protein level, and how to integrate that big data set. then various countries which are partner to these particular program, how they can collaborate, how they can come together to make this consortium, to share the data, share the knowledge, and come up with the solutions which could be beneficial for the all the countries and the humanities. So these are some of the major initiatives which is happening in our lab, and this particular term cancer moonshot was given by Joe Biden from US at that time, Vice President, which has led to the new research of the cancer proteogenomics in whole world. Idea is that for each patient wise we are creating database of their genome mutations and their protein changes, and all of those are really imparting new knowledge in the field of precision medicine. As I said, we do not want to work in the blinded manner, but rather we want to give the target therapies looking at the very specific molecules of interest. So at Iit Bombay, we are really involved actively with many faculty from different departments, from the different engineering discipline as well as mathematics department, who are all helping us and working together to look into how to really utilize this big data information, use artificial intelligence to really make good predictions, and also this could be converted to some good devices for the translational value. Towards this end, I went to NIH, National Institute of Health in US, and that's where we signed this MOU of ICPC with Dr. Henry Rodriguez, which led India to become the partner of this big cancer moonshot project. And we are now collaborating with several clinicians, several researchers and scientists from across the globe who are all looking into the similar kind of issues but sharing the data. And this is one of the Cancer Proteogenome Consortium group, which we annually meet. But likewise, we have a lot of ample opportunities in Iit Bombay to expand the scope of the learning, and really would like to welcome you to this new era of proteogenomics field, which does not have any boundaries, the way cancer do not have any boundary. Likewise, the field of cancer proteogenomics and field of proteogenomics does not have any boundary. It really requires a lot of interesting budding mind and enthusiastic students like all of you to really be part of it and contribute towards this part. As I said, in this particular space, when we look into the high throughput field of big data analysis, we also thought how to utilize this in the pandemic region, and we utilize that by developing certain newer approach of looking at COVID-19 diagnosis at the protein level from the mass spectrometers, and also we are applying different type of other approaches which can do the diagnosis of SARS-CoV-2 much effectively and probably much cheaper as compared to the routine diagnostics. But more importantly, we are looking at which of the protein biomarkers which can make prediction that how a patient who is coming with a mild COVID symptoms, whether they might be progressing toward the severe type of the symptom. And at the molecular level, at the protein level, can we identify and indicate which are the proteins or metabolites which are going to really change and this patient might be moving toward the severe type? Which are the possible repurposed drugs, already approved drugs, which could be utilized in this particular area? So all of these are kind of the field which we are like to expand. Also, some of you, I think, you posed a question briefly. I saw something on the vaccine. I would like to say that the vaccine targets are still need to be much more researched. We need multiple epitopes-based vaccines, and that's where the new understanding about looking at epitopes of the SARS-CoV-2 peptides using protein microarrays, which one of the project which we got funded recently, is going to be quite useful and provide new information. Finally, these are some of the recent publications. This paper just came today in the Nature Communication Biology from my lab, which is a good collaborative work from another faculty from our department and faculty from mathematics department and a lot of clinicians around to look at what makes malaria disease more severe and complex. And so again, the transition from the mild symptom and mild fever to the severe type. And this is a paper in Nature Communication which we published last month, which first time showed that what is the protein composition which makes us human, and at the 90.5% of the human proteome we are able to map in this particular large international initiative project. So a lot of exciting things are happening. Now coming to a slightly boring part, but the realistic part, you have to take the basic biology course BB 101 in the next semester, and I'm sure you will have a lot of hesitation taking this course, and you will have a lot of apprehension that what you're going to study in this course But at the end of the course, we are committed to change your mind, and we are going to give you a lot of interesting examples that how best you can utilize these applications for different type of applications, real life applications, interface of biology and other type of engineering discipline. We also invite many clinicians to interact with you and give you the real life problems in the course. Given this situation, we might invite them even online to interact with you and give you the exposure of what is really the major medical problems where engineering solutions are required. Also, we try to give you some exposure of the lab activities, even in the lab in this theory course, to give you some comfort that how these kind of biological data are being generated. But all of those together is going to be not the very conventional biology which you have been exposed and you did not like it. We will try to change your mind. That's all from my side today. So thank you for watching this presentation, and I'm sure you have a lot of questions. Let me have a look on the chat box and see what questions you have. Thank you so much for your attention.
Thank you, sir. It was a really nice talk. So I'll help you with a question in the chat.
Yes.
Will the treatment become more expensive because medicines will be made from start for each patient according to his or her genetic behavior?
No, medicine will not be costly because medicines are not going to be made overnight, right? Like you have seen even in the case of COVID-19, you don't have too many options of medicine. Medicines has to go through a lot of testing and the clinical trials and the safety efficacy test. So only the approved drugs can be given to an individual. But let me give you one example. So in US, in University of Washington, there was a researcher, Lucas Wortman, and he was suffering from leukemia, one of the blood cancer. And he was given the chemotherapy, which is prescribed and known for the blood cancer. But he was not responding well. He was, showing a lot of side effects, lot of toxicity, and even the disease was even, recurring again, repeated after treatment. So they had no idea that what is going on in this individual, how to treat them. So then he was a researcher working in the genomics field, and he thought, why not I sequence my own genome and try to look into what makes us so unique. At that time in US also, the healthcare did not allow to do these activities. But given his critical case and his knowledge in the field, they allowed him to sequence for his own genome. And after looking at his genome sequences, he was able to identify there are very unique mutations which are happening in this individual. For those mutations, now which are the available drugs which can treat that mutation? So that's where now they're looking for the list of approved drugs, and the drug repurposing concepts comes into the play. So for his particular mutation, which for that given gene where there's a defect there was another drug available from the renal cancer, which is the kidney-based cancer, and people have shown that for this particular gene change in the kidney cancer, if you give this drug, it's going to probably treat it better. So he was given sunitinib drug, and that actually immediately made the good wonder in his treatment, and he immediately got cured. He immediately showed the very good signs of recovery. And all this is only possible if you can look at things with much more microscopic view of what is exactly happening. Don't try to fit all the shoe size to every individual. Give them what exactly makes them so unique. All right. So more question: is it good to be part of this research on cancer if you do not have any previous knowledge on biological sciences till now? I think it's sometimes good to start very unbiased. You'll be also surprised to know that many of your seniors already do their internship and the projects in our labs, and we also want to see the fresh thoughts and fresh minds, how they can bring something which is very unique. So while you learn a lot of new things from working in these labs, we also try to get some of your knowledge and enthusiasm for learning the coding, the artificial intelligence based stuff, looking at different new devices, and of course those good interaction, which is very candid interactions, really help the research to move forward. And of course, you are part of the big teams, which is not relying only on one individual. A lot of clinicians, a lot of other scientists, they're all brainstorming to make some conclusions. So we definitely have no hesitation of taking students into some very serious project. In fact, right now, 10 students from your senior batch are actually working on the COVID projects, which are very serious. They're doing good contributions in that type of research as well. Is research in chemistry about molecules sufficient to take care of these projects because it's more of the chemistry than biology? I think, IIT Bombay is definitely one of the very progressive campus which offers you the opportunity to pick up the new knowledge and take the at least flavor of the new subjects, which is very common if you go to Harvard, MIT, Stanford, any of the leading world institute, biology, bioengineering, biomedical sciences. These are very advanced field, which very heavily driven by the engineering schools. And IIT Bombay definitely has made the big jump in that particular area. So here, you will get a lot of courses which is going to make you much more better understanding for this particular field. And many courses will be offered to you. Also, you'll have opportunity to take even minors in biology courses. So along with your major engineering degree, you can also pursue a suite of courses which can give you some parallel, the opportunities to learn the new subject and make more contributions. I don't see that you'll have any issues, even if you have a different background so far. I think, you're starting very fresh, so you can definitely take any knowledge forward. Does not sequencing genome take a lot of time and effort? This is something which I must say engineering field has made huge contribution in the next generation sequencers. So the first genome sequence project which happened in 2001 and 2002, that took almost 15 years time to sequence one genome of one individual. Over the time period, now the new type of technologies have come forward, especially the Oxford nanopore based sequencing and other type of next generation sequencer, which can sequence now genome in almost maybe a couple of hours time with hardly 50,000-60,000 rupees. So it will not going to take you a lot of time and effort. Every individual in future, when you're going to go to future medicine labs or the clinics, you are going to get sequenced. You're going to look at your profiles at the molecular and the proteome level, and that is going to help you to really think about how to treat this individual much better. Will stem cells become a viable treatment option in the future? Stem cells have already become reality in many fields. Of course, some of these things are still trying to reach to the more advanced level and reaching to more common level, but it is already a reality in many places in different clinics. I'm not sure if I have missed out some other questions, but if any more, I'll be happy to take. Okay, somebody had actually asked very interesting question. Please create vaccines so that we can come to campus. So I think you have asked a very candid question, and it is really a challenging thing to comment. Reason is that vaccine research and vaccine production goes through very strict guidelines, and you need to have a lot of regulatory approvals in place, lot of BSL-3 kind of laboratory facilities where the virus can be grown, where this kind of testing can happen. So you cannot do this thing overnight. Where we can contribute is essentially to look at molecular level how to treat a patient better, like those who are already getting infected from COVID, how best to provide some clues to the clinicians and doctors who can treat the patients better, how to identify the individuals who are high prone for the severe type of COVID, and even their mild fever, but can they move towards the severe type? Can we predict that and help those patients to have the better treatment? Of course, as we are going along, there is a lot of apprehensions about COVID vaccines, as you know. So how long the COVID vaccine which we are going to be getting is going to make an impact? Reason is that the level of the antibodies produced against this, how long it is going to stay in the body, how stable it is going to be. So neutralizing antibodies are going to really stay long, or they're going to be just for the short span. So far predictions is maybe 3 to 6 months time. Are we going to get another booster at that time? Is it going to again infect individuals even if they had vaccine? Can they again get reinfected? These are the very genuine questions which nobody has answered as of now, right? So still we need more research to look at, are there some vaccine can be created which has multiple epitopes. So for example, even if you are, right now you are targeting only specific epitope, a specific part, which is going to generate antibodies. Can you generate antibodies against multiple sites, multiple regions from the viral peptides, which could give us the long-term efficacy for the patients, for the individuals who will get the vaccine? So again, you are going to see a lot of new areas emerging, new discoveries happening in this particular space. It's not going to go so fast, but I'm sure we are going to welcome you very soon in the campus, maybe in the next semester. Thank you so much for staying awake and asking some nice questions. Muskan, any more questions or?
Thank you, sir. Yeah, it's done, I guess.
All right,
Thank you
all the
so
best,
much.
everyone.
Carrying further, I would like to call upon Professor Anand Rao from the Center of Technology Alternatives for Rural Areas department. He is also an IITB alumni with a BTech in Chemical Engineering. His research interests lie in climate change mitigation, carbon capture, supply chain analysis, etc. So, handing over to Professor Rao.
Am I audible?
Yes, sir, you're audible.
Okay. Good evening. I think this is really late in the night, and I should really thank all of you. I can't see anybody, but I assume there are some participants still remaining, including some of my colleagues. I really appreciate that you are still here listening to all these presentations, and it is really challenging to speak anything after, especially after Asim and Sanjeeva have presented such a nice work they are doing in their respective domains. Am I? Are you able to see my screen?
Yes, sir, it's visible.
Yeah, Prasanna.
Yeah, but I'm not able to see what I'm supposed to see.
Now it's not visible.
Is it there? Yeah, I think now.
Yes, it's there.
Okay. Yeah. First of all, welcome to IIT Bombay. And I don't know how many of you have been to campus, but this is how the entrance of the campus looks like. And I really congratulate you on you have made it, and you are here part of our community. Welcome to IIT, and we hope to see you in person sometime. So I'm going to talk about CTARA, where I come from, that is Center for Technology Alternatives for Rural Areas, which is a small center within IIT Bombay. So the main focus of this center is how to make use of technology for the disadvantaged sections in the society, especially the rural areas which are neglected from the mainstream development process. And for those of you who haven't been here, this is how the IIT campus looks like from a hill on the campus, and the small yellow dot is where our center is located. Just to give an idea, our center is working in highly interdisciplinary manner. So we are a bunch of about 10 faculty members, but we all of us come from very different disciplines. As it was mentioned, I have a background in chemical and environmental engineering, and many of my colleagues have very different expertise, maybe in social sciences, including water shed management, GIS, remote sensing, and so on. So our basic concern is how we can try to help the development process through the proper application of technology, and the focus has been on the bottom 80% who are in the bottom of the society. So if you see the world around, and especially in our country, as we see the overall development paradigm we see is in terms of the urbanization trend that we see, the consumption, consumerism that is growing, and then all of it actually is leading to unidirectional flow of resources, which is causing a lot of harm to the environment. And in this era of this rapid economic growth that India is boasting about, there is also increasing disparity across different communities within our society. And especially we can see the stark contrast between the city dwellers who represent India and the villages which represent Bharat. And so we have these overburdened cities and dying villages. And in all this backdrop, what is the relevance of education today, and especially the research in institutes like IITs? So here we are a small center having this humble effort to make sure that all the research that happens in these kind of institutes becomes relevant for the larger good of society. And in this, there is also one more query that we try to pursue is whether technology is always the part of solution, or maybe it can be part of problem as well. So there are different externalities of technology. So we have to understand what are the limitations of technology. And although we are going to be students of technology, we have to understand that technology alone may not be able to tackle many of the problems, because the problems don't come in the form of a chemical engineering problem or civil engineering problem or mechanical engineering problem. Problem is a problem, and you have to form a team, and typically it is an interdisciplinary team to tackle such a problem. So what we try to do is work on the interface of technology and development. That means we try to link the two concepts and try to see how technology can be helpful in the development process. So the mandate of CTARA is basically looking at the marginalized and disadvantaged sections in the society, and that mainly the rural areas are the ones which are highly neglected in the development process. The core areas like energy, water, agriculture, all these are the topics of research within CTARA, and mostly it is demand driven and need based research. So we first try to go to the field, try to identify what exactly is the problem, where is the shoe pinching, and then try to find the solution, and mostly along with the direct engagement of the stakeholders. That means we need to understand how exactly they perceive the problem, and they themselves may have different types of solutions or approaches, and we need to appreciate their traditional knowledge, and then using our scientific approach, whether we can combine the two and then form an amicable solution which they are able to accept. Because many times the solutions are developed in the lab, but the common people, especially in the rural areas, may not be able to appreciate or use those solutions. If you take a simple example of a cooking device, the traditional cook stove is supposed to be very inefficient, and there have been lots of efforts made to improve the efficiency of the cook stove. However, many of these models which were certified in the high-tech labs across the various institutes in India, they remained in the lab because people did not accept those solutions, because they did not take care of what is the need of the housewife who is trying to cook the meal for the household. And then we have to take into account the cultural aspect, the social aspects when we develop any technology solution. So we always try to engage with the stakeholders, and then we also try to involve the local institutions which help us to ensure sustainability of whatever solutions we are trying to promote. So research in CTARA happens across these different domains, right from water and sanitation, energy, housing, health and nutrition, food, agriculture, land use planning, and so on and so forth. So I'll just try to give you few avenues in which, although CTARA is essentially a postgraduate program, we have a MTech and PhD program in CTARA, but there are various avenues in which we do try to engage with undergraduates, and one of the avenues is a course named as Technology and Development Supervised Learning, TDSL, which is an optional or elective course the undergraduates can take right from their second year, and so through which you can engage in any socially relevant project which any faculty member across the institute can float. So CTARA is essentially a platform to where the interested students can work on these kind of interdisciplinary problems under the guidance of able faculty members who are interested from any domain. So the range of topics varies from water, energy, sanitation, public health, transportation planning, livelihood activities, etc. And you can see the website to get a hint of what type of topics are dealt with. It goes in 3 steps. The first step is the study, that is TD 390, that is the name of the course. The next step is the analysis of that particular situation, and then finally the student can pursue further if interested, and then take 12 credits for designing a solution. So this is the stepwise approach in TDSL program. And as listed here, there are just a few examples of the sample topics on which students have worked in the past, right from cook stove design, dissemination, cooking practices, soil and agriculture practices, biogas plants, brick making processes and practices. So you'll see many of these things are related to unorganized sectors and rural areas. So, for example, some of my students, we had undertaken the survey of the biogas plants already existing in the Thane district, which is a neighboring district to Iit Bombay. And we found that many of these plants, although we always understand that biogas is a very good solution and technology for cooking energy. However, there are a lot of limitations in terms of implementation and dissemination of this technology, and we have to go to the society and understand where the shoe is pinching. Similarly, another student of mine, many of the teams worked on understanding how the solid waste management is happening in rural and semi-urban areas. And then one of the dual degree student worked on assessment of waste to energy potential for such a small towns, because we always hear about such projects in large metro cities, but even the smaller areas, they do need some solutions. Excuse me. We also have in CTARA a project called RUTAC, that is Rural Technology Action Group. So which is a flagship project which is floated by the PSA's office, that is Principal Scientific Advisor to Government of India. And these RUTAC centers are there all across 8 IITs. And the idea is how we can provide science and technology inputs to non-governmental organizations and the rural areas, so that the development process can be enhanced in those areas. Finally, I would like to mention one specific program that the batch of 92 alumni have funded, and so they have initiated last year. This is called RISE, that is a rural immersion program specially designed for the students of science and engineering. So this is for the undergraduate students. So this is a unique opportunity to spend 2 weeks in rural areas. So it so happens that most of our students, all of you must be coming from urban areas. Of course, there is a small percentage of students who are also coming from rural areas. So for those students who never had an opportunity to go to rural areas, this is a chance for you. And the objective is to expose and sensitize students to the problems being faced in rural India, and think about what are the possible solutions. So the idea is not to find the solution right away, but just to observe and experience the rural life. So that is the main motivation of this rural immersion program, and it will provide a platform, of course, to support the students who would like to further explore developing the technology-based solutions to the problems they experience when they come back. So you can either through TDSL or any other mechanism work on those issues that you identified during your stay in the field, and then work on those. So unfortunately, because of the COVID situation, we could not send any students during summer, and I doubt whether we can send anybody this winter as well. But otherwise, we are planning to offer these 2 times a year, both in the summer and winter vacation. And many first and second year students, as well as some graduating students, also participated in the last 2 offering of this program. I think my 10 minutes are almost over. If time permits, I'd like to just play a short video which will introduce you to this program. Is that okay?
Yes, sir, it's fine.
Yeah, go ahead.
Okay. I hope the link works.
Sir, the video isn't audible. So, like,
Oh, I'm sorry. What should I do?
So you need to go into the share option in the above bar, and there you need to go from files like web share.
Okay, it was visible but not audible, is it?
Yes, sir.
But I don't have it as a file. I'm just playing it from YouTube. Will that work?
Okay, sir. I just need to check.
Okay. Otherwise, I just share the link and then students can see them, sir.
Yes, sir, that could be viable too.
Okay. So then shall I stop?
Sir, it is still not audible.
So should I stop it then?
Yeah, maybe Professor Anand, you can share that link, and
Yes.
yeah, attendees
Sure.
can see that later.
Yeah. Yeah, I'll do that. Okay, so this is the link which is here, and if you go to CTARA website, you will find the link to RISE program, and the link is included in that web page as well. So I'll welcome all of you to take a look at it and then participate in this program whenever it is offered next time. And I'm really sorry, probably I overshot the time and then it's quite late, but if you have any questions, I'll be happy to address them. Thank you.
Thank you, sir.
Yeah.
Last but not least, we have a presentation by Krishi Mantri, who is also an academic coordinator for EnPoWER, stating the research opportunities available in IITB.
Oh, I always thought that we have Krishi Mantri with us during this presentation.
Yes, sir, he's also an academic coordinator. Rishi, are you available?
Yeah, Muskan. Is my screen visible?
Yeah, it is.
Yeah. Uh, a very cheerful, a very cheerful welcome to everyone present here to IIT Bombay. You had a lot of questions initially about how are we going to approach professors, how are we going to get projects. So here is a small presentation over that. Before that, I would like to introduce you to the sub-part of Undergraduate Academic Council, which is the team EnPoWER, which actually is the research wing of Undergraduate Academic Council, and we are the student team which is going to help you to get all the research opportunities and help you to get many research opportunities to your doorstep. So yeah, we all know for IITians, research and science is something which is really important, and this is actually true for most of us IITians. So, like we all know, IIT provides a huge amount of opportunities. Like we have 16 departments, 19 different centers, 4 interdisciplinary programs, School of Management, so many high-tech labs, world-class research opportunities. But the main question is, how can undergraduate students get to these opportunities and get an opportunity to explore research? So here are the most important ways in which we students approach professors and get projects. First of all, with the help of events by EnPoWER and Undergraduate Academic Council, and second, by directly approaching the professors. So I'll iterate on both of these points and tell you like what are the different programs we have through which you can get projects and how can you actually approach a professor. So first of all, we have two important undergraduate research programs, which is summer undergraduate research program and in-semester undergraduate research program. And there is a centralized portal where a lot of professors float many projects from various departments, and you can actually opt into various projects. And this actually helps in promoting interdepartmental projects or many interdisciplinary projects, and you can actually explore a lot of departments through this program. My screen. So these were the two portals of this year, tolling ISERP and SERP, where there were projects from various departments. To know more about it, you can scan the QR code, or you can actually search ISERP on Google, and then you will go to the website of ISERP and the projects floated this year. Next, how are you going to directly approach a professor? A lot of you had a query that how are you going to approach a professor? There is a simple 3-step procedure which most of your seniors and most of us follow so that we can get a project by a professor. First of all, we call it a databasing. Is first of all, you need to check what interests you, what are the field of interest, then go to the department's website and explore and try to locate professors who have research interests which you find compatible with yours. There you'll actually find all the research interests, their work, their papers, and also their email addresses. This is one of the example of mechanical department website. Second of all, you need to write an email to the professor to meet, to take an appointment, and you need to write that you need to express your interest of why do you want to work under him, on what topic do you want to work under. And it is always like better you read up some basic material about the research field of the professor before meeting. We all know that IIT Bombay professors are really cool, and they actually are really hospitable, and they'll always call you for a discussion, and then you can discuss with them the possible projects, and they actually accommodate you to many different projects at a very large scale and give you a very huge amount of exposure. So to ease this process, we have a novices guide on the EnPoWER's Facebook page, which can actually help you through go to all the steps which you require to approach a professor while to take any of the project. We also have a sample mail for you in the novices guide. We also have a curious community discussion group, which is a group of research enthusiasts from all over the institute, where there are many interesting discussions and about various projects. And there are also some small groups known as SIGs or student interest groups having specific research interests, which you can join. You can scan the QR code and join the curious community group now, which can help you to know about various opportunities in IIT Bombay. So I request you to please scan the QR code, or you can just search Curious Community on Facebook. You will get the group. Next, I would like to make you aware about the department research coordinators. Every department in IIT Bombay has a research coordinator whom you can contact, and who will actually help you to get in contact with various professors and relevant seniors whose interests match with yours, and then who is actually going to be a very important point of contact for you in the department when you need to seek any research opportunity. We are the team EnPoWER, and we are always here to help you to get any research opportunity or any other doubt in any other academic query of yours, and you can always contact us. So at last, these are our social media handles. The Facebook EnPoWER page is where you will get all the interesting research opportunities available, or our events, and also the video for today's video or the recording of today's session will be uploaded on our Facebook page. So please scan the QR code and follow our social media handles to get the best updates on research in IIT Bombay and all our events. Really thankful for your presence. I would really like to thank all our enthusiastic professors to show such good interest and enlighten the students about their research. I would also like to thank Professor Pratibha Sharma to actively participate and manage this event with us, and also the team of volunteers and the audience, which was really very patient and went through the session really well. I really thank you all and for the session to proceed so well.
Okay, so Krishi, we are done with it. So towards the end of the event, I would like to thank all the speakers for sparing their time for this event. I would like to thank all the student volunteers, IRCC team and EnPoWER team for helping in coordinating this event. And last but not the least, all the students who have attended this event, UG students. And I hope that you have got a lot of information from the presentations about the research which is being carried out at IIT Bombay, and got some motivation to work in some of the areas that we tried to touch upon today. Thanks a lot to everyone. And we hope to see you soon in the campus.
Thank you, guys. So the recordings and the PPT will be shared on our Facebook page. You can find it there. So we can end the session now. Thank you so much for your presence. Good night.